Fantastic. Okay, well, good afternoon. Welcome to the Continuum part of the multi-scale modelling course. I'm right in saying you've only had one quantum session so far, is that right? And then everything else is going to be next week. So what I'm trying to do this week is to keep it very much limited to the Continuum part of the course. In the next two sessions towards the end of next week, I'll try to link it back to some of the molecular stuff you learn next week and show it how it fits within the kind of broader framework of multi-scale modelling. But today, really just to focus on the continuum and partial differential equations and the type of equations you're going to have to solve within this approximation. Okay, so the plan for the entire course, I'll talk a bit today about the kind of broader context of where the continuum fits within the larger modelling hierarchy. Try to explain the continuum assumption, and we'll talk a bit about this because it means a kind of specific thing in this context. Most mathematical models you've used will be based on the continuum, so it's worth being clear exactly what we're talking about here when we talk about the continuum. And then towards the end of today, we'll talk a lot more about partial differential equations and to do with the numerical solutions of these. So the idea here is we're going to sort of lay the groundwork here. I'm hoping this is not entirely new to you guys. I'm hoping you've done at least some of this before. And the idea with this is that will set the groundwork so that then when we move on to talk more about the Navier-Stokes equation, we talk about solving fluids in a continuum, we can actually build up the complexity. But the kind of basic principles are going to be covered today. Next session we'll talk more about basically the key assumptions, and this again is in light of the course you'll have with Fernando. So on molecular dynamics there are a number of things that are kind of more complicated that you actually assume away when you're talking about something like the Navier-Stokes equation that's used in most fluid dynamics applications in industry. And then in session 3 I'm going to talk more about how we actually link the two together, and then hopefully we'll get to the point where we can actually solve the Navier-Stokes equation on a computer, or at least get an idea of how that would be solved in practice. Okay, so really by the end, the key kind of outcomes for this for you guys should be to state the continuum assumption and specifically identify that it's actually for continuous fields. So that's an important distinction and one I'll probably labour maybe too much. And then explain how this underpins fluid dynamics and how the equations we use are based on this assumption. We'll cover today the kind of introduction to this, but hopefully by the end you'll be comfortable with three-dimensional fields, vector calculus and partial differential equations, and how to solve those. We're going to focus, the majority of the kind of solution is going to be numerical here for this course. The reason for this is because that's actually the most useful way of solving these equations in general. Hopefully you'll be able to state the Navier-Stokes equation, identify the key assumptions, the meanings of the terms, be able to simplify this and solve this in the kind of simplified cases. And with this, hopefully an understanding of how this has linked to the kind of lower level models, molecular dynamics in particular, because that's the next one, but maybe quantum, and then also how this would fit within, say, plant scale modelling, which we'll cover again next week with Niall. Yeah, and this kind of place within that. But today we're just going to try and cover the meaning of the continuum assumption, and again this idea of continuous fields, how to plot fields, and this is where we're going to use basically the computers to actually explore the fields and look at how we plot them, either using Excel or using programming, depending on you guys and your background. And then just an introduction to some ordinary partial differential equations, solutions of those, and then hopefully we'll build up a bit of code so that you've actually solved them yourself. So just to get a feel, how much of that sounds like terrifying or too easy, or can you give me some idea? So who here has worked with the Navier-Stokes equation, for starters? Okay. Who here has solved differential equations before? Okay, brilliant. And who has done programming? So in MATLAB or mostly MATLAB. And then, has anyone not done programming? Any programming at all? Okay, good. So hopefully we can work with that. So there is a way we can do this today with Excel. But going beyond, we'll get far more interesting results by using various programming techniques. Okay, so this is kind of the obligatory picture for any multi-scale modelling talk. Personally, I don't really like this because I think it's oversimplifying the situation, but you'll see this in most talks on multi-scale modelling. And the idea here is you have a kind of length scale on the one axis and a time scale on the other axis. And then you talk about the range of validity of your various paradigms. So your quantum mechanics, as you've already seen, is down here at the kind of nanoscale, the angstrom, very, very short time scales. And then there's some overlap here. So this is where, you move away from the kind of full quantum complexity and start to assume, in an average sense, classical mechanics is valid. And this is where molecular dynamics, so this is basically Newton's law solved lots and lots of times for individual particles, and you'll see next week. Then you've got this kind of mesoscale, and this can mean kind of a range of different things. So it's kind of a statistical approach. You've got Boltzmann's equations, you've got various forms of, say, SAF's associating field theory. And I think George will cover some of these next week. The continuum usually is put here, and this is what we're going to focus on. Now, everything you work with a continuum approximation is actually non-dimensionalized in fluid dynamics. So the actual range of validity is not necessarily always clear with this, but essentially most people assume it's valid over kind of this range. Generally, the range you can actually apply it to is also limited by your computational power for most cases. And then at the top we've got this kind of idea of plant scale. So this is kind of solving things as flow diagrams where maybe the continuum is part of this, maybe not. Okay, so historically I'll give you a kind of quick overview of basically the background for this. So on the left here we've got the kind of proponents of molecular theory, and on the right you've got basically a selection of the people from continuum theory. And it's fair to say that these guys here are pretty much most of the people who believe molecules exist up to about the beginning of the 20th century. This is just a very small section of people who use the continuum. Now, I mean, I think arguably the continuum approximation makes sense, right? You kind of feel a surface and it's solid. It feels like it, is made of a continuous substance. So this idea that, everything is actually made of molecules is a hard sell. And it was made originally by Democritus back in ancient Greece. And it generally fell out of favour. You've got Aristotle here who was kind of arguing against this, and actually his worldview effectively prevailed. You've got guys like Dalton here in the 16th century who kind of put forward the theory that things could be made of molecules, and again, didn't really get much traction. Someone like Boltzmann proposed it, but only as a kind of tool, if you like, to make the theories work. And he ended up actually killing himself because no one would accept his viewpoints. So, these guys have kind of really struggled to push this idea of molecules. And it's only when you get to Einstein who actually starts to show this kind of Brownian motion and the kind of existence of kind of particles at a smaller scale that you actually get people starting to believe this. And then this is coupled with kind of Thomson and showing X-ray scattering and this proof that there is actually a kind of individual discrete nature of reality. Now obviously at the same time then quantum mechanics comes along and everything becomes more murky. But generally what's happened then is you've got these kind of molecular view of the world, and I've put here Leonard Jones, who's kind of one of the founding fathers of what is currently molecular dynamic theory. So, within this we've got a very small number of people, and at the same time this entire theory has been developed for the continuum. And the continuum, based on this assumption, it kind of underpins mathematics. It's this assumption you can define derivatives. It's this idea that everything is continuous, which means it works mathematically. And you've got Euler here, who's kind of pioneered so many different things. Many things are named after him. In the centre here you've got Cauchy, who developed a lot of the kind of underlying continuum theory, more in solid mechanics, but it's still relevant to fluid mechanics. There's some work by kind of pure mathematicians on the underlying theory of the continuum. This is Cantor, just as because he did so much work on this. And then for us today, the two people who kind of developed the equation of interest, Navier and Stokes. Navier on the left here and Stokes on the right. And they developed the equation at different points, but for some reason it's named after both of them. So the key picture is the two kind of frameworks developed independently, and you've kind of got this entire continuum theory developed with no idea that a molecular nature exists. So it was only recently that people started to realise that actually this assumption isn't the only description of reality. And for a very, very long time, this is kind of not believed at all. Okay, so I want to show you this video. This is something I actually put together for a competition a couple of years ago. It just gives you an idea of the kind of research I've done. Partly showing you because it's a nice video, partly because it kind of shows these links between the molecular and the continuum. And this is what I work on, the kind of links between these two. So this idea that you could have kind of a load of molecules together and some sliding walls, and then the overall behaviour when you zoom out far enough and you have, say, 300 million molecules all together, is this kind of behaviour where you start to see this kind of bulk overall motion that actually looks very similar to a continuum. So there's a comparison here of the molecular and the continuous. So you can actually see, despite not being able to see the individual molecules, the overall behaviour is actually kind of on average, this kind of complex turbulent-like behavior that varies spatially, varies temporally, and basically is extremely complicated. And the idea here is that, you know, the overlap between the two is far from clear, and this is a kind of something I'll come back to a few times today, where it's not actually clear. So this is showing the nucleation of a droplet, and this is again using molecular dynamics. So you'll see more about this next week. But what you can see here is this kind of formation of a droplet, coalescence, and, you know, on a surface here is effectively what you'd see at the continuum, and you'd just see a kind of formation on a window, for example. So these kind of collective molecular behaviors are kind of moving together, and then if you average them all, you get some kind of bulk behavior. Here we're looking at kind of slightly more complicated molecules, a selection of different surfactants in a liquid bridge, and what you see is the overall behavior here is them stretching and then it breaking. And again, this shows very good agreement with experiments. So when you look at the kind of a liquid that looks like a continuous substance breaking down, this kind of bulk molecular behavior actually looks very similar. And the final case here is boiling. So if you heat the bottom wall here, so this is like if you heat a pan on a stove, what you start to see eventually is the kind of formation of bubbles. So this is regions where the evaporation locally pushes the kind of bulk liquid away, and you get a formation of a gas pocket. If you take an average of that surface, you can start to see that this bulk molecular behavior starts to look like a continuum. So the kind of take-home message from this is that really, when you describe things with a continuum, you are describing the kind of average behavior of lots and lots of molecules. And, you know, the nice thing about this is the continuum is much easier to solve. It's much cheaper to solve, has a lot of nice properties. You'll see from molecular dynamics, it's far more expensive. So you can see here the kind of formation, and this is from molecular data, but you can see it's kind of convincingly like what you'd see in a continuum. Okay, so the key equation, and we won't get to the full complexity of this, we're going to look at just this last term today, by the end of today, but is the Navier-Stokes equation. So this isn't the full picture. It's valid for single phase flows and Newtonian fluids, and I'll cover next week what that actually means, but briefly it describes effectively the flow of a fluid in the same way that Newton's law works. So you've got some time evolution here, which is called an unsteady term, so this shows how the fluid evolves in time. You've got a convection term, and this describes basically the flow of fluid and how that carries the momentum inside the fluid. And this is the term that's responsible for turbulence that you see in many, many cases of interest. We've got this pressure term, so this is the kind of pressure that you're used to when you hear like weather reports, or, you know, the pressure you feel when you change altitude in a plane, for example. And a local action of this will actually cause a flow. So this here is a term that kind of represents that. And then finally, you've got this diffusion term, and this is if you drop some ink in liquid, this will be what causes it to spread out. So the various terms in this describe basically the overall behavior of the fluid. So there's a lot of complexity here. It's a nonlinear partial differential equation describing velocity and pressure. Each of these terms are vectors, so it's actually 3 equations shown here. So what we'll do is we'll build up to this, and by the end of today we'll hopefully have at least an idea of the various terms in terms of the actual differential equation, and you'll have at least an idea of how we'd start to go about solving this equation numerically. Apparently this equation is impossible to solve directly. Certainly any solutions you get, even for very simplified cases, are so complex you can't really express them with any kind of simple closed form expression. And in fact, there's actually an open problem to prove that there's existence and smoothness of this equation, and that's worth £1 million if anyone can solve it. So it's a complex equation that we're not even sure is actually valid in every particular case, but it's extremely useful for many, many fields of fluid dynamics. You know, planes fly based on this. Cars are designed in Formula 1 using this equation. You've got weather prediction, pretty much this is the cornerstone of that. So it's used in many, many applications, and it's used because it works. So any questions about that? I mean, we're a very small group, so feel free to butt in if there's any questions. Something's not clear, please just stick your hand up or shout out. If that's okay, then we'll move on to the actual subject. So how are we doing for time? Yeah, fantastic. Okay, so definition of a continuous function. So if you go to a textbook on analysis, so the kind of fundamental underlying mathematical definition of what is a continuous function, here f of x. What they'll say is that f is continuous if and only if you have this limiting case existing. So that is, as x tends to c, f of x tends to f of c. So this assumes a couple of things. First of all, it assumes that f at the point C actually exists. That is, you can actually define that function at every single point on that line. It also assumes that you can actually reach it by taking that limiting case. Now, this is kind of hidden within this, the kind of underlying principle, all of mathematics in many ways. So the fact you're defining a function that's smooth and continuous, makes these implicit assumptions. And you can imagine as you start to get the kind of discrete nature of reality that this potentially can be a problem. There is another definition, Epsilon-Delta Definition, which actually makes the statement that the closeness of x is less than epsilon and the closeness of the function is less than delta. I'm not going to cover that, partly because I don't understand that. It's a very kind of mathematical, formal way of working for this. But if you're interested, it's well worth checking out just to kind of understand kind of underpinning. But for me, this is basically a definition. It's an assumption. And the reason it's such a common assumption is it works very, very well in most cases. So this really is the underpinning of the majority of mathematics. When you're talking about the calculus, differential equations, derivatives, integrals, the implicit assumption is that this function, you can define these kind of continuous functions. And like many assumptions, it kind of doesn't always get stated, but it's well worth being aware that actually your equations, your Navier-Stokes equations, the validity of what you're doing is only true as long as this condition is true, or at least some form of this condition is true. So just be very, very aware of the kind of assumptions that you're building up, often without actually realizing it when you're introduced to these things. So the reason this is very useful is because it allows us to define derivatives. So let's go back to the kind of definition of a derivative. That is, if we take some function, and we take that function at a further point delta x further away. So we've got, say, a point x and x plus delta x, and our function is f of x, and then the function at x plus delta x is given here. So I'm sure you've all seen this. This is kind of the thing you're shown, at various points, and then you ask, will this be on the exam? And you're like, oh, forget it. So it's kind of this underlying principle behind the derivative itself. And I just want to restate it here because it's actually going to come up again and again in what I present today. So the way to think of this really is it's basically just a definition of a gradient. So if you think about the definition of a gradient of a line, a straight line, what you do is you take the change in x and you divide the change in y by that. So the change in height divided by the change in length there, and that gives you the gradient of the line. So you've seen that in defining a straight line. You're doing exactly that. So your change in y here is basically going from f of x to x plus delta x, and the distance you go is a delta x. So it's basically defining the gradient at a point. Now the thing about this is we're actually assuming the gradient at that point is a straight line. That is, we've zoomed in far enough that the local description is actually a straight line. For this kind of simple varying function, you can see that looks fairly reasonable approximation, but obviously it's not going to be exact. So what we aim to do is then actually make that delta x slightly smaller. So we zoom in, we're using the same approximation, and now this gradient is an even better representation of the gradient at that point by zooming in. And again, this kind of definition of the gradient at any given point is kind of worked out in this way as an approximation. In a limiting case, that is, as delta x tends to 0, we get this definition of a derivative. Now, if this makes you feel uncomfortable, it probably should. It's this kind of weird, contradictory idea that you can actually take a delta x that's so small, but yet still have a line that you can actually define a gradient for. It's kind of a contradiction in terms. So typically what you're doing here is you're actually defining this notation, df by dx, to actually be a kind of a placeholder, if you like, for this kind of limiting case. This idealization, if it's possible to zoom into a given point where you have a kind of small infinitesimal difference, then you can define a derivative at that point. And this is the kind of fundamental principle of the calculus. So, as we're talking about a continuum, I think it's very worth being aware that actually this is a mathematical idealization that doesn't actually exist in reality. You can never zoom in far enough. If you zoom in far enough, we get to molecular dynamics, we get individual particles. Zoom in even further, we get quantum mechanics. Even before that, we've actually got kind of fractal lines, which means that actually maybe this approximation isn't valid. So just be aware that it's an approximation. It's one that works very, very well, but it is an approximation. Okay, so any equations which include derivatives are differential equations. So for example, if we set df by dx equal to 0, that's a differential equation. And hopefully you know how to integrate that. You just integrate both sides, split the variables. And, differential equations can be many different forms. So in this case, they can be equal to ax plus b. You can get second derivatives, which, you can solve in the same way. They're also, the way to think of differential equations is they are the same as any other equation. They just happen to have basically derivative terms in there, which means they're more complicated to solve, but in principle they are just relating, some f to some x. That's their entire purpose. So if you think about two kind of very common equations, the equation for a line, y equals mx plus c, or Newton's laws, they are actually differential equations. So your definition of the gradient is dy dx. In this case, because it's a straight line, this is a constant, but the actual form is a differential equation. And Newton's law itself is actually a differential equation. So, you're used to dealing with these as just kind of letters and numbers and not worrying about the kind of form of those, but, they are, if you want to look at them in that way, differential equations. So a bit of terminology, equations, the highest order derivative is known as the order of the equation. So here, 3 for this equation, 2 for this one, and 1 for this one. And this is very, very important if you're trying to solve these analytically, if you like. And if you've done any kind of course on mathematics in engineering, you would have solved, integrating factors and second order derivatives and all of these type of things. This is the reason why you quantify them, and this is the reason why you try to solve them. Today, we're not going to do any of that. We're going to basically just go straight to numerical solutions, partly because they're much easier once you get your head around them, and partly because the actual number of equations that can be solved exactly are very, very small. So it's a very select number of very kind of idealized equations that you can actually solve. So one class of equation that can't be solved directly are nonlinear equations. So roughly speaking, these are any equations where your unknown value, in this particular case f, so this is f as a function of x, so f we don't know and we're trying to find by solving these equations. If that f is actually multiplied by another value of itself, then it's a nonlinear differential equation. So for example, f times df by dx here, d2f by dx squared, is actually a nonlinear term. This squared here is a nonlinear term, and then this derivative here squared is a nonlinear term. So generally speaking, if it's a nonlinear differential equation, you're not going to have much luck trying to solve that directly, apart from some very specific examples. So the reason why differential equations are interesting, they are everywhere in modern physics, and particularly physics of the continuum. So anything where you're talking about differential equations, you are assuming something is continuous in order to have defined these equations, as we've already seen. And then what you're doing is you're actually expressing quantity. So the wave equation, for example, specifies how a wave propagates through a substance. Advection diffusion shows how some chemical concentration advects and diffuses through a substance as a function of time, for example. And Newton's law, as we've said, is actually a differential equation evolving in time. So, they're actually valid useful in many, many areas of science. Just mention quickly how we can solve them exactly. So, if they're linear, we can solve very simple equations like this. For example, if df by dx is equal to a, we can just integrate that directly by splitting variables. Does everyone know how to do this, right? Yeah, okay, fine. And then for second order differential equations, we can do the same thing. And again, this idea that most are too complex. Okay, so how do we solve these numerically? Well, if we go back to our definition of the derivative, df by dx is equal to some limit where delta x tends to 0 of the difference between f plus delta x and f divided by delta x. Now what we're doing here is we're making delta x arbitrarily small, and in that limiting case we can get this kind of calculus where we can differentiate and integrate in whatever way. However, we can actually relax that approximation, and we can say, hang on a second, if we make delta x reasonably small, and the smaller we make it, the closer we get to the solution we want, then actually we can start to get an approximation for this derivative. So let's take df by dx, and we actually just approximate it with as the gradient, effectively, in this way. So what you can see is you're taking, for some delta x, the value of f of x and f of x plus delta x, and we're actually taking with a difference of delta x between those two, and we're using that to actually define an approximation for that derivative. Does that make sense? We can do the same thing for second order derivatives. So this process does the same thing. It effectively relaxes the approximation and then expands that form. By the way, all of these slides will be on the blackboard. So just for shorthand notation, we're going to introduce this notation here. So there's nothing new here. It's basically just a definition. So what we're saying is if we've got a form of x plus delta x, we're going to replace that with subscript I plus 1. And if it's f of x, it's just subscript I. Similarly, if we've got x minus delta x, we're going to replace that with I minus 1. So this is just a slightly more concise notation that saves us having to write out each time the fact we're taking x plus some small increment. We're actually saying we're taking fi at some point I, and we're adding some increment. And this assumes implicitly that delta x is constant throughout the domain. So we're always using the same increment, which means we can use the same value of I. Is that okay? So replacing those equations, you can see now df by dx is written quite nicely and concisely in that way, and d2f by dx squared is written in that way. Okay, so what this now means we can do is we can take our differential equation, df by dx is equal to a. We can approximate df by dx as this I plus 1 minus fi divided by delta x, and then we can rearrange. And this allows us to get the value of f at I plus 1 by taking the value of f of I plus a times delta x. So we're simply just taking this expression here, substituting it into here, and then rearranging to get fi plus 1. So this gives us a kind of algorithm, if you like, a way of getting the value of f at I plus 1 from the value we know of f at I. And just by rearranging this expression, we can actually then get a kind of equation or a process for getting the next value of f at I. The same process can be done for second derivatives. So what we're doing here is this second order differential equation. We replace it with this form, and then we rearrange again to get I plus 1. Notice in this case we have to know f at I and f at I minus 1 in that case. And we've got a dx squared from that rearranging. So what we're doing here is we're basically saying if we know the value at f at I, then we can get the value at f at I plus 1 using this equation. This f of I plus 1 is equal to fi plus a times delta x. Once we know the value at f of I plus 1, we can then get the value at I plus 2. So hopefully it's clear that from this, knowing one single value in your domain, you can then get the expression at every single other point in space, just from that single value. So in other words, what we've got here is a way of solving that differential equation. So if you think what you do when you solve a differential equation, you are effectively getting f as a function of x. So that's an expression for that allows you to get the value of f at any known value of x. What we've got here is a numerical approximation to exactly the same thing. So that means that for as long as we know one single value of f, we can then get every other point by basically just keep incrementing and working through the function starting from that point. Okay, so we're going to do a hands-on session where we're actually going to play around with this. I'm aware that most of you probably have used MATLAB. Has anyone used Python before? Okay, great. So I'm going to do the solutions in Python, but if anyone's using MATLAB, hopefully the syntax is similar enough. So this is a comparison of the two side by side. Generally, if you're using MATLAB, hopefully you'll see most of the things are kind of fairly similar. For guys who use Python, forgive me for using this kind of star import. It just makes it clearer that the two are very, very similar. But hopefully commands like linspace are clear. If they're not, then we'll discuss in the hands-on. And then you can see things like plotting functions are very similar between the two. So hopefully the examples are clear, but if anything isn't, please stick your hand up and I'll go over it. Just a couple of notes on the differences. In Python you do for I in range, and then you specify this range, whereas in MATLAB you do for I equals 1 to n steps, for example. Python uses 0 indexing, so the arrays start from 0, whereas in MATLAB it starts from 1. Probably the key difference here is this indexing notation. So you use square brackets in Python where it's round brackets in MATLAB. And then the one other thing about Python is that you don't actually have an end statement. For loops, the scope of functions are done by the indentation. So again, if there's anything not clear, please stick your hand up. But that's just to give you a kind of brief overview for the hands-on. So we've got a range of questions here. So starting off, we're just basically going to use this definition of a derivative and just kind of get comfortable with that by working out simple function like x cubed and using this kind of fundamental definition to actually calculate that. Just identify the order of a few differential equations and identify if they're linear or not. And then part 3, you basically take Newton's law for constant gravity and integrate that using the initial conditions x equals 0 and initial velocity. And then repeat that process solving it numerically. And then you can actually compare the two solutions and see whether or not you get a reasonable approximation. And then finally, we'll start to look at what happens when you start to get nonlinear terms in your equation. Now this isn't strictly a nonlinear equation, but it's a slightly more complex form of equation. So you can start to see what happens as we get more complicated behaviour. Okay, so is that clear? We've got about I reckon about half an hour at least for this. We'll see how we get on with this. So the first two parts are easy enough to do on paper, and then the next parts will either require you to write code, or you can do it on Excel if you feel more comfortable. And then what I'll do is I'll go through the solutions in about half an hour. But anyone has any questions before, or you can stick your hand up and I'll come around. Okay. So what I'm doing is I'm running this in what's called, it's a Jupyter notebook, so it's just a way of running Python. And you can see we get a similar plot to what we had before with Excel. So, you know, instead of basically taking successive cells and then working out the value in the next one, we're redefining a variable each time. So we're doing exactly the same thing here with the code. We're taking the previous value and the value before that, we're adding the time step squared, and then we're saving that in a new value each time, and we're moving through in that way. So you either do this as a series of successive cells that you take the previous one and you add to that, or you're working through an array and calculating it from the previous values with a loop. And then the end result is the same. So that's okay? Any questions or? Okay, so the next part was to take the same approach, but this time we're adding in an extra term, a 1 over x to the minus 1, or 1 over x term. And you can see, depending, what's quite interesting about this is actually now this is a nonlinear equation, which means that the behaviour we get is actually dependent on the initial condition we choose. So for example, if we take an initial condition that's 0.01, like this, I'll show this as a straight line. You can see it's increasing. We make the initial condition 1, again it's increasing. If we get a value of 0, we've got a division by 0, and that actually looks like that. If we get a minus value, it drops like that. So we get very different behaviour depending on our initial condition. Sorry, bear 1 second. Oh, I know why, sorry. Okay, well, I'll move on, but yeah, play around with this, because generally you get very, very strange behaviour. What I'll do is I'll include these snippets of code in the solutions. By the way, just out of interest, would you prefer these as MATLAB, the code snippets, or are you okay with Python and translating? Who would prefer MATLAB? No? Okay. Okay, fantastic. So that's just an example of how we then solve those differential equations on a computer. Okay, so if we move on now to talk about fields and partial differential equations. So the idea now is we're basically going to take the same concept and apply it to slightly more complicated equations. I'm aware that a lot of you look kind of slightly worried. Is this kind of beyond anything you've done before, or completely new, or? Yeah. So you've never done anything like this, sort of differential equations, solving, approximating? About 4 years ago, okay, that's fine. Yeah. I mean, the problem is with anything, it's only easy if you've done it recently, and only easy if you've done it before. So my suggestion is then between now and next week to just play around.
Can you upload after like the code and so on, like the slides?
Yeah, of course, absolutely. So what I'll do is I'll upload Python code. I'll also upload the Excel spreadsheets as well, so you can play around with it. And my advice, really, I mean, the only way to get your head around these things is just to play around with it. Try changing these values, see what they do. Go through, derive, I mean, effectively, it all comes from this kind of approximation, this derivation of approximating your derivatives and then reordering them and then just using that to calculate the next value. So once you get your head around that, that's the kind of basis of everything we'll go through. But really just understand it's a way of solving differential equations where, you know, you're effectively using a particular value and then stepping through from there. Okay. So, we've talked about Newton's law. Now, Newton's law is not what people would call a continuum equation. In fact, it's actually used in molecular dynamics, which is a discrete description of reality. And in molecular dynamics, you're solving Newton's law for each of the individual particles that are themselves evolving, you know, continuously in time and in position. But that would be referred to as a discrete system. So this idea of a continuum is not exclusive to continuous systems. When we talk about the continuum, this kind of part of the course, the continuum hypothesis actually is referring to the nature of fields. So that is this kind of physics concept of a field where you have at any point in space the ability to define a value. And, you know, probably the most common one that people think about is like the magnetic field. So you stick a magnet and you see a kind of iron filings, for example. What you're doing there is you're effectively describing the field with the shape of the iron filings and the way they move around. But, you know, conceptually, people describe that field as being able to probe at a particular point. And at any given point, you can actually get the value of that field. So in fluid dynamics, we use the same concept to describe a flow field. So this is, like you see on the weather reporting, for example, you know, these fields of arrows and movement of fluid. You're describing it effectively as a continuous evolution of some, you know, field in three-dimensional space. And so the implicit assumption here is that we have so many particles in a given box. So this box here is effectively so large with so many particles that we can treat it as a continuum. The discrete nature is no longer important, or at least is kind of averaged and smeared out. So in practice, if we have 1 meter cubed of air that has 10 to the 25 molecules, this means we have a phenomenal number of molecules, which means that this approximation works extremely well. And in fact, actually, this works very, very well, even down to much smaller system sizes. So we can actually still treat things as a continuum down to a few thousand molecules in some cases. So that picture I showed originally, actually the continuum approximation is actually valid to much, much smaller scales. So the question is then, when is this not true? F is some continuous function. We said before, if and only if this limiting case exists, where we can tend to the point C, f of C actually exists, and f of x can actually reach that in that limiting case. So the times when it stops being true are kind of physics cases. So mathematically, this is an idealization, it's always true. But in terms of physics, there are many cases where this isn't true, and this is when the molecular nature of the substance becomes apparent. So an extreme event like a shockwave, for example, a nuclear blast, would start to break down the kind of continuum approximation. You'd start to see the effect of individual molecules. When you're near a boundary, so when you're actually, you've got a fluid flowing near a wall, you've actually got a moving fluid, and then you've got a stationary wall. And at some point, that must go from moving to stationary. And it's far from clear where that is. And certainly in a continuum approximation, that kind of transition is not well defined. This gets even worse when you've got an interface of, say, a soap bubble, for example, or a droplet, where you've actually got an interface between a liquid and a vapor. And when that meets a wall, so this is called a three-phase contact line, and in that particular case, you've got a very clear example of where the molecular nature, the non-continuous nature, if you like, starts to become important, become apparent. And then arguably something like a fractal is quite an interesting example. So this idea that you've got these shapes that no matter how much you zoom in will always continue to effectively reveal new structure. This whole assumption of the continuum hypothesis is actually based on being able to zoom in to a point where you've got a straight line. And the question is, are they still valid? And most things in reality are fractal. So then is this continuum hypothesis a good model for reality? So these are all kind of interesting questions. To my mind, probably not ones that people actually know the answer to, and the basis of a lot of modern research. The Knudsen number is something that comes up quite a lot for a metric for when you know that your substance has to be described by molecular dynamics. For me, this is only useful for dilute gases, and that's very, very dilute. Cases like space shuttle re-entry, the edge of the atmosphere, very, very dilute systems. When you talk about dense fluids, and these are most fluids of interest in kind of chemical processes, the Knudsen number is not too meaningful. I mean, this talks about the mean free path, so this is how far a molecule will fly relative to the kind of length scale of your problem. In a dense fluid, everything's packed together, so what you actually see is that it won't fly at all, but yet still it's not clear if the continuum is valid. And this pictogram basically shows what I mean here. So if you've got three molecules, and you effectively try to approximate them as a continuous function, arguably that's not going to be a very good approximation, and you've only really got three individual values at the location of those molecules. So, there are cases where this breaks down. Okay, so we talked about the examples of a field. So it's the continuum approximation means the continuity of a field. So what is a field? It's basically a two-dimensional description of something, or two or more dimensions. There are three-dimensional fields, as well as fields in time. We're going to focus just on two-dimensional for clarity here. We'll take a simple example here where it's basically a polynomial. So this is some function of x and y. In this particular case, it's a polynomial that's x squared plus x plus y squared plus y. This cross term, which has both x and y, and then some constant. So it's effectively a polynomial in both x and y. And what this means is we have an expression which varies in either direction, in both x and y direction. So one way to think of this is actually as like an Excel spreadsheet. You've got a set of values in x, a set of values in y, and then what we can do is we can actually use each of those values in x and y to calculate the expression at the appropriate point in space. So I'll show you that as a spreadsheet. And so we've got our coefficients here, so what we can do is we can adjust these. So let's say we set both coefficients a and c equal to 0. What we've effectively got now is a function that varies linearly in both the x and y direction. So you can see it varies linearly as we move in x, and it varies linearly as we move in y, for example. If we set b to 0 as well, we can actually see now we've got a function, actually for clarity I'll set. Let's set d to 0. Yeah, okay, so now you've got a function that's just varying linearly in one direction. So we can vary, if everything else is 0 other than, say, the coefficient here, you can see it's just a linear function. So it's just a description here, if you like, a useful mathematical description of an underlying two-dimensional image. And to be honest, actually, this is kind of what you use every day when you actually use an image, is exactly that. It's basically two-dimensional information, x and y components made of pixels. So each of the individual pixels has some value. And it's exactly the same concept here. The difference is we've described it using some mathematical function that describes each of the points. And this is used in some of the kind of compressions for photos, is they actually try to re-express pictures as mathematical functions that are kind of simpler and easier to express in terms of memory use. So does that make sense? Is that clear as a concept? So what we do now is this same trick, where in the limit that we've got each of those individual Excel spreadsheets, imagine we have a spreadsheet that just keeps getting bigger and bigger and bigger until we've got an infinite number of values, where each of those values is infinitesimally small. In that particular case, we go to a continuous function. So it's the same concept we had in 1 dimensions, now extended to 2 dimensions. So this function now is continuous and valid at every single point in space. Bear in mind that we've only got 2-dimensional, so the x and y are basically the 2-dimensional coordinates. We're just showing it using a 3rd dimension here, just kind of to express it or show it valid. So show it here as a kind of valid expression of that. Maybe clearer is to think of it as a contour plot. So this idea of a kind of picture, if you like, so that different x and y values, you actually have different values depending on where you are, and each of those has a different kind of pixel, if you like, and In the limiting case, you can define that function at any point in space. So now we're going to use the same trick. Instead of taking the difference between 2 points and getting the gradient, what we're going to do is we're going to define a kind of patch, if you like, that's got delta x by delta y. And then we're going to actually use the difference between the left-hand side and the right-hand side to define a derivative. So just getting rid of that picture in the background, we've got this, considering just the x components first of all, we've got this element that has a width delta x. So what we're doing is taking a point halfway across, so we're adding delta y over 2. This has a height of delta y in each case. And what we're doing is we're taking x and x plus delta x. So it's effectively a cube, and that cube has width delta x, and we're actually using the function either side of it. So what we can do is the same, conceptually the same thing we did before, where effectively we take the function at x plus delta x and the function at x, we divide it by the difference between the two of them, we take a limiting case in order to define a derivative. That is the change in that function over that element, if you like. Now one thing we've done here is we've actually used the same value of y in both cases. So we've actually got y constant, and this is a partial derivative effectively. Now every partial derivative you see implicitly is holding the other variables constant. So df by dx is partial derivative with respect to x, where y is held constant. And I've just written that explicitly here. In the y direction we can do exactly the same thing. So we're using the x plus delta x over 2, the halfway point, and we're taking a y value and y plus delta y. And again we're taking a limit that delta y tends to a point. So this idea that you've got this small patch, if you like, and it's getting smaller and smaller and smaller, and in a limiting case we get a derivative here where x is constant. So what's that doing? Well, for this kind of surface, which is a two-dimensional function, the derivatives are effectively defining how they vary along a line of constant x. So for the y derivative, how it varies in y along a constant x, and how the x derivative varies along a line of constant y. So let's go back to our field. How do we use these in practice? Well, because we've got a nice mathematical description of our field here as a couple of polynomials, a polynomial in x and a polynomial in y, we can then actually calculate our derivative. So the way we do this is effectively just holding y constant, so we treat everything that's y to be a constant as well as the constants, and then we differentiate just with respect to x. And we can take the first and second derivative. The same with y. Again, in this case we hold x constant, and we take the derivative with respect to y in that particular case. So by defining this continuous field, we can then apply the calculus in the same way we could do in 1 dimensions. Now we're doing the same thing in 2 dimensions. The key point here is because it's in 2 dimensions, we actually have to hold one of the directions. So if we're differentiating in x, we hold y constant, and y we hold x constant, effectively. So what that means is we can actually then use the same trick we used before to define numerical derivatives. So what we're doing is we're taking that same approximation, and instead of taking a limiting case again, we're using this approximation where we're saying, f of x plus delta x is approximated just by this difference between the two. And we're not taking a limiting case. And then again, we're introducing the same notation, so I plus 1 and f of I. We've also got this second notation for j, which is denoting the y direction. So you can see the j components are j plus 1 and j. So this here is just notation, that is kind of shorthand for this. And the idea here is we're basically defining these derivatives, where I've dropped the kind of holding constant part. We're defining them basically as approximation in this way. So I just want to mention quickly how we plot these fields in 3 dimensions. And this will be the first part of the hands-on exercise. This is an example in Python. Probably this is slightly easier in MATLAB. You can also incidentally plot contours in Excel. If you select a region in space or a field, as we had in that example, you can actually plot those fields as a contour in that particular case. But this example here is in Python, and it allows you to basically plot this. We have to define a mesh grid. So this mesh grid is similar conceptually to this array of values we had to define. So what I'm doing here is I'm defining each x value. Let's take an example here. So for example, what we're doing is that is calculated from the x values here and the y values here. So it's just like a convenience function that contains each of the x values, the corresponding y values. And then from that we can actually calculate the function at that point in space. So generally you'll see this sort of same expression, mesh grid, quite a lot when you do MATLAB code. We're calculating just the polynomial function and then we're plotting it as a surface. For the contour, it's actually much simpler. We do exactly the same code, defining the mesh grid, and then it's simply just a case of using contour F, if you like, or there's a range of other different plotting options there. Okay, so for this part, effectively, the hands-on session is going to be based on the computer. The first thing to do is actually just to plot those fields using those snippets of code you've just seen. It's a slightly different field in this particular case. So it's a function of sines and cosines multiplied together. And your range of values for x are between 0 and 1, and your y is 0 and 1. And then you're going to evaluate the partial derivatives both directly, so by hand, using the actual function, the underlying function here, and then calculate the numerical derivatives as we had before, and then actually compare the two answers. And then start to look at what happens as this approximation improves, so as you get kind of finer resolution in that case. Does that make sense? Has everyone done some plotting before in MATLAB and things? No? Okay, give me a shout, I'm happy to help. And by the way, Phil, I think now probably is a good time to take a break, so feel free to get up and walk around for a bit, because we've been so, bear me 1 second. Okay. So again, on this web interface, so the first thing we're going to plot. Okay, so we've got here first of all the plot of contour F. Here, so play around with this and just see if you can get it working in MATLAB. What I'll do, like I say, is everything will be MATLAB next week, but we're basically plotting F here as a product of sines and cosines and showing that. So let me just evaluate that and show you the expression. We're also defining here df by dx, which is, like I said, a cosine and then sine. And we're going to plot both of those as well. So let me just uncomment that. Okay, so the plot of the actual function itself is this top one. This is a plot of f of x. Its derivative in the x direction looks like that, and its derivative in the y direction looks like that. So these are just calculating, basically just plotting these expressions here. So when you manage to plot the f, hopefully this should be easy enough to plot. And then the last part is to basically try to compare that to the numerical derivative. So the concept behind getting the numerical derivative proceeds in the same way that we saw before. So the idea is we're actually starting okay, maybe I'll delete that. Still going to end up confusing you. And I'll put it in the solutions and you can play around with the different forms. But effectively what we've got here is what's called forward difference. So it's we're basically calculating I and j from I plus 1 and j plus 1. So if you remember the form of the equation in the slides, we're effectively using this approximation to get the next value from the previous value. So that's exactly what we're doing here numerically. And we're looping over all of the values in I and j. And we're calculating basically the numerical derivative for each of those. And then what we're going to do is we're going to overlay the contour of the derivative we calculated exactly with the derivative we've calculated numerically in both cases. So let me show that. So we're calculating the derivatives directly. Oh, here we go. So maybe it's not clear because I've got it too high, but what you've actually got here, as you can see, it's not really clear on this projector. Let me do a lower. So let's say we take a number of points to be equal to 10, for example. So this would be quite a low resolution. And what you can see here is the actual numerical solutions are actually kind of a coarser approximation to the underlying function. So the numerical solutions are actually giving us kind of a less good approximation than these exact derivatives we've worked out using the calculus. What we can do is we can actually increase the number of points. So let's stick this up by an order of magnitude. And this is basically the same as decreasing delta x. So we're going towards this limiting case where we've effectively got an exact derivative. What you can see now is actually the two solutions are very, very close. So you can still see, hopefully, there's a slight difference here between the two. But on the whole, the two are a pretty good approximation for derivative. So what I'll do is I'll upload those solutions. And what I'll try to do is I'll try to get them in MATLAB so you guys can actually use them directly. But the key thing you should see from this is basically that the numerical derivatives and the analytical derivatives are actually giving the same thing, but only in a limiting case. And one thing you can do is you can actually take the error between the two. So you take away the result from numerical and the result from the analytical, and you can show that actually in a limiting case, as the delta x or delta y gets smaller and smaller, the error gets smaller and smaller. And then if you go to the limit of precision, effectively the two should be identical. Yeah, and here's just a kind of bit of code that shows that plot. Okay, so basically the idea of this is you should have 3 hours where you actually work on this afterwards if you've got time. What would be good is to actually just make sure that this works. So what I'll do is if I upload the solutions, you can download them, try them, just make sure you understand them, make sure you understand the way they work, because we'll build on this in the next sessions. So the final part is basically to apply what we've covered so far. We're going to look at solving a partial differential equation. So a partial differential equation, in this particular case, is describing the way the function f varies in space. So it's a second derivative in x and a second derivative in y. And this is what's called Laplace's equation. So it's an equation that actually describes the diffusion of a substance. So let's say you put ink in water, the way it spreads will be described by Laplace's equation. This particular form of it will give you the solution at the end, or at the point at which the ink is fully spread. And direct solutions of this equation are typically used in electromagnetics, in potential flow theory, so it's a useful equation for a range of different scientific applications. And what we're going to do is we're going to look at solving this numerically here. One note on the notation here is that we've dropped the x equals constant and y equals constant from partial derivatives, but they're always there. So when you see a partial derivative, it means that everything else but what you're differentiating with respect to is held constant in that case. So Laplace's equation is actually written in a number of different ways. You might see it written as del squared. So this nabla operator, as it's called, or del, is effectively d by dx and d by dy. The squared means it's a second derivative, which is also sometimes written as an upside down triangle as well. So you might see both of these notations. You might also see this subscript notation. Often these can be replaced by indices that imply summation. So there's various forms and notations, but really the key point here is that in any form, this equation, we effectively are solving this written out explicitly. Now this is the two-dimensional example of this. Now in practice, we actually have 3 spatial dimensions as well as an evolution in time. And we'll come back to this next week where we actually look at solving it for time evolution, probably just in 2 dimensions still. So there are a number of analytical solutions. We're not interested in those today. What we're going to do instead is just look at numerical solutions. So recall our approximation for the second derivative here, where we effectively get a form where it's plus x, minus x, and then 2 times the expression there divided by delta x squared. And the same for df by dy. What that means is we can actually rewrite these using the notation we used before of I plus 1, I minus 1. And j plus 1 and j minus 1. And effectively what that gives us is what's called a 5-point stencil. So you can think of this as being a value at the centre, I and j, and then what we're actually doing is we're including the values either side of it. So this kind of makes sense. If you think about what we're doing with a derivative, we're taking 2 points. We're using those 2 points to calculate that derivative. In this particular case, we're doing it in two directions. So in x, we've got these 2 points either side in x. In y, we've got the 2 points either side in y. So we're using those to effectively calculate our derivatives. So now what we can do is we can actually just substitute in these approximations to the derivatives directly into Laplace's equation. We can rearrange to get it in terms of Fij. So this is just purely mathematical manipulation, which we'll do in the hands-on session. Effectively just rearranging this just to get it all in terms of that. And then if we approximate or use delta x equals delta y is equal to 1, just for simplicity, this whole thing collapses. This horrible term here collapses to 1 over 4. So what this means is we have a method for going from each of the surrounding points to calculate the new value of Fij from that. So the way to think of this is if we've got, the values at +1 surrounding that, we can actually calculate the value of Fij using these expressions. So it's basically the y component and the x component. Once we've got that, we can use that value to calculate the next one. So it's the same concept we used before with Newton's law, where we took the previous values and kept calculating the next ones. We're doing it in 2 dimensions now. So we're taking the previous value and then we're using the surrounding values to calculate the next one at the centre, if that makes sense. Now before, when we talked about initial conditions, so that this idea that you had to specify the initial position for Newton's law and then you calculated each of the values from that initial value. In 2 dimensions, what that means is we actually have to specify the top, bottom, left and right of our 2-dimensional domain. As long as we know those, we can then use those to calculate the values at any point in the domain. So what we do is we start here, let's say in the top left-hand corner, and we update f12 by taking, say, the 2 boundary conditions, as they're called, as well as the 2 internal points. Once we know that value, we can then update 2,1 by using that and the value we've already calculated for 1,2. And then the next value for 3,1 from those values, and so on until we've updated every single point in our domain, working through. We then repeat the process again. Now one thing that will happen is because depending on the initial condition that you specify, this field will say be initially 0, you have to keep iterating until you've got a solution that satisfies all of the boundary conditions. So effectively we have to put all of this inside a larger loop that keeps iterating until we get a solution. In Excel you can actually turn on iteration. In the options there's an option to actually have iteration. So if you're using this in Excel, you could think of these as each individual cells. If iteration is turned on, what it will do is iterate until you get to a solution or it reaches the maximum iteration you have. In order to iterate, you should basically be checking that each successive value that you calculate in your domain minus the previous value is basically less than some particular error. So this idea that you keep iterating until you've got a solution that's to a level of precision that you want. You're never ever going to get an exact solution. This is a numerical solution. So the idea is you iterate until you get as close as possible to that. So this notation basically says we sum up all points, all 9 of these points. We sum up the previous iteration, all 9 of those points, and then the difference between those two should eventually tend to 0. So it should stop changing. Once it stops changing, it means we've got our solution. So the final part of the question is basically to take Laplace's equation. First part is basically to derive this, so just substitute in and manipulate mathematically to get that form of the equation. And then using Python, MATLAB or Excel for 9 points in this particular case, using iteration, which you have to turn on in Excel or you actually explicitly have to do in Python, go through and try to solve this for a range of different boundary conditions. And what I'll do is before next week is I'll actually upload the solution to this, but I'll give you a few days just to kind of play around with this yourself to try to solve this. Really this is kind of the end point of today. So hopefully you can see that these various bits are kind of building towards something. So the first part is one-dimensional version of this. The second part is defining a field. And this third part is taking that field and actually using these differential equations and solving these differential equations to get a solution for that field based on the boundary conditions. So if you understand each of the 3 bits of this, hopefully this part kind of brings that together. I think part of the problem is most of the issues you're having will be to do with coding and actually getting it implemented rather than probably the mathematics of this. To give you just a hint as to how to get started on this, you're effectively having to specify boundary conditions. So in this particular case, you'd use a notation like this, which is specifying all values. This colon specifies all values for the 0th index. In MATLAB, that would be 1. The bottom are going to be equal to some value, left, right, and top. And then what you do is you actually loop over all of the internal points. So it goes from 0 to n points. So we're actually looping from the internal points 1 to n points minus 1. And we're just simply calculating this expression that you saw here to update each of the Fij's. And then we're just doing that again and again. So this whole block here will be iterated until we get a consistent solution. So what do we got? We've got about 20 minutes left. So what I'll do is I'll quickly go through the summary, and then you've got... I'll leave it till 5 minutes to the end before going through. So we've got about 15 minutes for this. If you want to instead work on the previous one, you're more than welcome to do that. And then give this a go afterwards. What I'll do is I'll go through this solution at the start of next week. So next Wednesday, I think, our next session. So next Wednesday, I'll go through how to do this and explain this. Any questions? Does that make sense? So in this particular case, what we're doing is we would copy the value the other side of the domain. So it's something like n minus 1, like that. I'm not sure if you can do that in MATLAB, but it's that kind of idea. And then this one would be 2, like that. So the idea here is we're actually copying, wrapping our domain round again. So it's a bit like if you ever played Asteroids, where you go out one side, you'll come in the other. So it's kind of periodic in that case. So try that out and see what happens with that as a solution. Okay, so let me just finish off. So today's session, we've seen hopefully what the continuum assumption means. And the crucial point here that I want you to take away is that it describes a continuous field. So you use the continuum throughout all of mathematics. The concept of the calculus is based on this approximation, but the key point for what we're talking about here when we talk about the continuum is continuous fields. So these fields in 2, 3, 4-dimensional space, if you like, in time, are what we're describing. And this assumption at any point in space you can effectively zoom in and define derivatives in this way, exact derivatives, and you can approximate them numerically. And the crucial difference between this and molecular dynamics is that if you zoom in far enough, you get to the point where the molecular nature becomes important. So by using the continuum, you're making the assumption that the molecular nature is not important. We have enough molecules, we can treat them as a continuum. So be aware of that. I've had introduction to fields and at least in principle how to plot them. Please try that. Please persevere and get that working, because that would be very, very useful in what we do from now on. We've introduced some simple ordinary and partial differential equations. We've shown a couple of analytical solutions, but really the emphasis has been on trying to solve them numerically, using this trick of rearranging the derivative and then using that to kind of calculate the next value. And then we talked about solving that with either a programming language of your choice or Excel. One other thing I just wanted to mention in passing, just so I can link this back to the Navier-Stokes equation, is when we talk about two-dimensional fields, for example, we've only talked about scalar fields. So these are fields that at each point in space they have a single value. And this is, pressure, for example, concentration of a chemical species. For something like the Navier-Stokes, it's actually a vector field, which means that at each point in space there are 3 components of velocity. So you have your velocity, and you have this concept of streamwise velocity or wall normal velocity. People use these kind of phrases, but effectively at each point in the field, x, y, z, and t, you actually have a 3-component vector. And then when you start talking about stresses, which we probably won't come to in too much detail, but then you start to have 9 components. So just to be aware that actually there are scalar fields, and then you start to talk about more complicated vector and stress fields where each point in space has more than one value. Typically we would represent these vector fields using arrows. So at each point in space there is in 2 dimensions, for example, there's a u and v component. So this would be like when you're watching a weather forecast, for example, you start to see wind maps, and they are vector fields, showing where the wind will blow to. So this kind of shows, basically at each point in space, the u and v component as an arrow from that point. So it's this idea of a kind of vector arrow, but at each point in space arbitrarily. So hopefully at least from weather forecasting you've at least seen these. But what that means is that the Navier-Stokes equation, we've actually focused on this last term here, and this is Laplace's equation, if you like, when it's equal to 0. But it's this second derivative here of u. We've done it for a single value, but the principle is exactly the same. This equation is actually 3 separate equations. So we've solved effectively one of those equations for Laplace. So I'm sure hopefully you appreciate now there's lots of complexity here. And we'll start to break this down further in the next few sessions. And what we'll try to do is look at some of the other terms and how we solve those. But I mean, this was always going to be, the starting lecture was always going to be kind of getting these concepts in place. Solving these extra terms is basically the same concept. So for example, hopefully you can see that this term we can actually approximate using our forward time derivative. There's actually this term as well. We can actually, well, that's actually more complicated, but certainly this term we can start to use some of these ideas that we've already seen to approach these various terms. And in doing that, we can actually approximate the Navier-Stokes equation with numerical solutions. So just coming back to our overall picture, we kind of covered in this first session where we are in the wider modelling hierarchy. And I've kind of emphasised again and again, this continuum idea. This really is this set of assumptions, and we fit within that kind of particular location with molecular and quantum at the bottom, and then plant scale modelling towards the top. And really for the continuum, these partial differential equations and solving them numerically are the currency. They're the way we actually approach the problem and describe the physics of the problem and then get solutions. And this is the basis for the entire area of CFD, which is used throughout industry to solve problems. Next week we'll talk more on partial differential equations and the numerical solutions of these. We'll talk a bit more on two-dimensional vector fields. What I'll do is I'll get the MATLAB solutions, I'll upload them, and then we'll go through them again at the beginning of next week so we can review and hopefully get everyone at least working with those particular things in MATLAB. And then we can start to move on from there. I'll also talk about the derivation of the Navier-Stokes. So that's kind of going to be more mathematical, less computational, just so that we can understand exactly what's assumed in this, the kind of key terms, what they mean, how we simplify that to actually then get back to things like Laplace's equation, and you can start to solve it in some special cases. And then towards the end, once you've had the lessons from Fernando Bresme on the kind of molecular stuff, then we can start to talk about how we actually link these to the molecular dynamics. And hopefully we can get to the point where we're actually solving the Navier-Stokes equation, or at least a form of it, numerically. So I've got a few books suggested for further reading. For differential equations, I really like this. There's also an advanced version of this. It may not cover it in too much detail, but as far as a kind of mathematical review, this is very, very nice, just because it kind of goes step by step. So there are so many books on fluid dynamics. I quite like this one. It talks about the numerics, how you actually approximate things, everything you can imagine you'd ever need to know. It's also got quite a nice derivation of the Navier-Stokes equation and all of that. There's also this website that's actually very, very good. It's called a 12-step guide to the Navier-Stokes equation, and it builds up term by term, a solution of that equation. And in some ways, the kind of process we'll follow will be similar to that. So if you want to get an idea of where we'll go next, that's well worth looking at. And then these are a couple of academic papers. This one I think is very, very nicely written, kind of philosophical. There's a few by this author, and he's kind of does these review papers where he talks about where the continuum fits. So if you're interested in this, if you're interested in going into this as a research topic, fully recommend reading this. It's kind of quite a nice light introduction to just the topic of multi-scale modelling. And then in terms of how you actually link the two, for me this is the kind of key paper, how you actually link, say, molecular or discrete. This is not an easy read. It's statistical mechanics, 6n-dimensional phase space, all of these things, but it's from the 1950s and it's kind of beautifully written paper, so it's worth taking a look at if you're interested, especially if you're going to go into research. It's worth seeing what's out there. So I think I'll see you next on Wednesday, and it's 9 o'clock session this time. You guys have got my email, right? If there's any questions, if there's anything you want to know in the meantime, give me an email. Are you meant to? Do you know if you've been told if you have staff contact hours outside of this, or not? Do you know if you're? Because I'm actually based in this department, so were you meant to have contact hours outside, or not sure? Okay. Well, I'm on email, so if you need to meet up and chat about anything with this, give me an email. I'm happy to come and meet up and give you some help with this. But otherwise, I'll see you next Wednesday.